Hello, everyone. Thanks for coming this afternoon. My name is Jimmy, and today I want to talk a little bit about avoiding microservice megadisasters. Is everyone ready for story time? I love afternoon story time. So this talk is mainly a story of a company I worked with for about a year and a half or so to help turn around their ship from the impending iceberg that was their microservice megadisaster. So in order for me to tell the story properly, we have to really go back in time and talk about how the company started and how their IT infrastructure grew over time. Now, to protect the names of the innocent, I've changed the name of the company, so we'll be talking about Bell Computers, not any other computer company you may be associated with. It's totally unrelated. So what we have here is a picture of their IT system in the mid-90s. Does anyone recognize what this is? It's a mainframe. It's an HP tandem mainframe, and I guess they actually still make these things because you can still go buy them and get support from them and things like that. Bell Computers, as they started to grow over time, they needed to build a system to help manage all of their orders, all of their entire company. And so they went with the most common solution at the time in the 80s and 90s, which was a gigantic mainframe. And this mainframe held every single piece of information about the company. Everything that could possibly be transacted through the company was held inside of this one single mainframe. So we had sales, catalog information about the different products they had, orders information, their CRM, like everything to do with anything with the company was in this one system. And that was okay because they didn't have any other system to place an order except for mail order catalogs, or you could call them up and place an order over the phone. Now, of course, over time, the system got larger and larger, and more junk was put in there, and of course, COBOL is not the most expressive language in the world, so this eventually became the what's known as the big ball of mud, big ball of poo, or the monolith. So around the year 2000, they decided, you know what, a lot of other companies have websites that actually do stuff. Maybe ours should be a little bit more than just call us to place your order, and so they decided to build their first actual .com e-commerce website. Now, the design of this initially was, I thought, pretty good. The original Bell.com design consisted of a number of top-level websites or subdomains of an individual of the entire application. So you had catalog.bell.com, you had account.bell.com, you had orders.bell.com, and search.bell.com, all these distinct ASP.NET 1.0 web forms applications built each with their own individual database, and at some point they all had to communicate with the back-end system. All fulfillment and all the orders actually getting processed still had to go inside this single mainframe, so all the supply chain, all that other junk was still going to be inside that mainframe. But the front-end website, these had individual applications and individual databases. Now this is how they designed the system. The reality was more like this, where everything called everything else through API calls or SOAP calls or just embedding someone else's DLL in your project, or what was happened very often with these kinds of source control systems. I would just grab other people's code and just shove it inside my project and then complain when it broke later on. SQL 2005 introduced the concept of linked servers. So I didn't show it here, but there's also arrows between each of these databases as well, because what's wrong with joining tables against different physical databases? If you can do it, if you weren't allowed to, or you weren't supposed to do it, then why did they give you the feature? It doesn't make any sense. So while they had some separation now between the different logical areas of the system, this again turned into now a distributed ball of mud, where I had different little balls of mud, and each of my in different applications. And of course, the big one was still actually back over there. Now, the funny thing was, this mainframe was not built by Bell Computers, it was built by a competitor. So it was really fun to see the competitors' consultants come in when they ever had to maintain this mainframe, because that's kind of embarrassing if your competitor has to support the system that your entire company is built on. That's pretty ridiculous. So, looking at this application, they decided, of course, let's throw it all away and let's do the rewrite. Now, this existing application was in production for about 15 years, which is a very long time for an ASP.NET Web Forms application. It accepted orders worldwide, so you can place an order in one country and have it shipped to another, things like that. It generated billions of dollars a year in revenue through this one application. A very significant portion of the company's revenue came through their .com website. Millions of orders a day at its peak, Black Friday typically, But they found that there was really no way forward with this existing application design, that because everything was talking to each other and everything referenced each other, it was really, really hard to make any sort of meaningful change in this application. And they found there was one particular business request that they just could not fulfill that was going to force them to really throw away the entire application and start something new. And it was this idea that although it supported the ability to accept orders internationally, you cannot place an order in one country, bill it from a second country, and have it shipped to a third country, which is pretty common for global companies, but you could not do it through the existing website. And so they were forcing you to go through the phone to do so. And so if you're a big corporation that needs to order computers over the phone, you'd probably try to find a competitor as well. So this is about the time you started to see more and more people talk about service-oriented architecture and microservice architectures as well. So naturally, they did the smart thing and just read blogs of other people and just tried to blindly do what those other people did. One of the pictures they really liked was this concept of a Netflix-oriented architecture where you have very small microservices that can connect to each other via APIs, standards-based approach, and they saw, that's great, let's go ahead and build this architecture. They wanted to have some core principles around building this architecture. First of all, they used to have a really big problem with data being shared between multiple different places. So they had a core tenet of no data duplication. I cannot ship data to somewhere else, and if you need some information, you have to come to me to get it because I am the source of truth. We're going to see this one come back in a little bit about how that really screwed things up for them. They wanted to follow those service-oriented architecture principles of isolation and autonomy, that individual services were isolated from each other. I didn't have people sharing code back and forth, things like that. They wanted to use web APIs for absolutely everything. So if you needed to get data or needed to affect change in another system, you must go through a web API. And the last big one was to get off that mainframe with a project called Bell on Bell, as opposed to Bell on competitor hardware. So 18 months. They built a system around these sort of core principles and had a pre-production go live where all the developers came in over the weekend and they turned on all the servers, connected everything up, and flipped the switch. So after 18 months, hundreds of developers on Bell's top hardware, they flipped the switch, went to the website, and nothing showed up, which was rather embarrassing for quite a lot of people. So they said, okay, that's odd. We expected to have some response because we've been running this application on our laptops for so long. Why is it failing now? So they did the sensible thing and threw money at the problem. So, okay, let's go ahead and put everything on one single gigabit fiber backplane, Ethernet rack, everything super connected to each other, very low latency, and let's upgrade all the servers to, you've done this on their website, right, where you go to the servers and try to make the most expensive machine you can, or is that just me? So they did that. They said, let's just go, let's go make the most expensive machines we can with the insane amount of RAM, connect all these things up, reinstall everything, get it all configured, and still nothing happened. So they had a suspicion that maybe there were some timeouts that were happening. So they decided to go to all of the web configuration, all the API configuration, and update all the timeout settings to a maximum infinity timeout. So we're just going to sit and wait for something to happen on this website. And they waited. And they waited, and they waited, and they waited for 9.5 minutes until the website finally loaded. And this is just a simple page showing a list of products for one of the catalogs. Around this time, they also said maybe we did something wrong, so that's when we got involved to try to help them try to fix the situation. Now, the first thing we had was 18 months to ship anything is not micro. If you have to take 1.5 years to ship an application, then it's probably not a microservice or micro anything. It's probably something much larger. So we had a post-mortem after this, also known as a retrospective, also known as a blame-storming session, to figure out exactly what went wrong here. And we had a few clues. One was they were completely saturating their network traffic with all the API calls going on. And by the way, with a normal application, like a normal monolith, if you will, if something goes wrong, there's an exception or crash, it's really easy to figure out what went wrong because you have a single stack trace that tells you everything that's executing at once. With this kind of architecture where everything is an API call, there's no one stack trace. I instead have to go through tools like Wireshark or other network monitoring tools to figure out, okay, for this one request, what in the world happened with this one single request? So we took just that one simple page And in about 2 weeks' time, we pieced together the puzzle of exactly all the different calls that were being made. And we found that they sort of misinterpreted this picture slightly. So in this picture, we have the idea of that there's one single external request that hits a service, and then I make a number of internal service request calls, and they get back to me. Now, what's not supposed to happen is that any of those other service calls can't make additional hops. That is, they have to be able to service that request all by themselves, and they can't go anywhere else to get that information. Well, that's not what they did. This picture looked like some sort of cascading, insane graph of calls, because every single one would call additional services, and those services would call additional services. Those services would call additional services, and almost to infinity, well, not to infinity, about 1,000 different network calls for that one single request. So this picture for them was just basically a filled-in green circle, because everything was calling each other. We also found cases where services would call each other as well. Service A would call service B would call service C, and then service C would also call service A. And now I have a distributed deadlock. It was really, really fun. So with this picture they had, where I had a single request calling thousands of API calls, and we looked to see if they had any resiliency built in, things like the circuit breaker pattern. No, of course not. If any one of those API calls failed, the entire request failed. So we're doing some math for them. Say you have each API call has an SLA of 150 milliseconds. Now, because they were using Windows Communication Foundation, WCF, that pretty much already, any one request already hit that SLA, because there's no WCF call that can take less than 150 milliseconds, it turns out. And they wanted to have a 99.9% uptime, which is only 3 nines. That's really not that great, but they thought they could achieve that at least. So in this one request that made, let's say, 200 different requests, the absolute best case scenario they could have was 30-second response time to get that page to be shown. So immediately, that's just absolutely impossible. But we also look at the 99.9% uptime and do some probability math around this. If you look at 99.9% uptime times 200 calls through my probabilities class that I took in college, we find that that site has a 0% chance of ever being up. So this architecture was doomed from the start. The original architect was naturally fired. Aha, just kidding. He left before this went to production to spread his mess somewhere else. And we went and asked the developers, like, how could you possibly make it 18 months without ever seeing this one problem? And I said, well, look, we're all adhering to our 150 millisecond SLA, and they had the charts to prove it from that one single request. And I found that the way they were calculating their SLA was only calculating the code that they ran. But if their service called another service, they wouldn't count that time in terms of their SLA. So, of course, everything running in their one process was going to be under 150 milliseconds, but having to call to someone else was going to add time that they just didn't calculate. So the first lesson was you either have to own your SLA, or your SLA is going to own you. And, of course, they were completely owned by their SLA. The next thing we found is they had understood the whole concept of the fallacies of distributed computing, but they missed the first part there, the fallacies. They actually thought that all these were just things that were okay to pretend like they're true. So network being reliable, they just assumed that was true. Latency being 0, we assume that's true as well. Bandwidth is infinite, absolutely it's true. Because, again, everything worked on their machine. Why did it work on their machine? Because when they were doing local development, they never, ever hooked up external services. They faked out all of those external service calls, mocked them out of whatever you want to do, so that they never had any network hops when they're developing locally. They would just have some local cache. So, of course, it worked great locally, because I never made any network hops. But as soon as you try to build a system that has to make those network hops, it would have been immediately apparent. So for 18 months, they never actually tested locally to even see, like, what will this be like if I have to actually hit those other services? Nope, worked on their machine. Let's go ahead and ship it. Now, this picture they had here, even looking at the service boundaries they drew, were all incorrect. And we'll come back a little bit later about how they got into this incorrect service boundaries. But I can kind of see why. If you look at some of the literature out there trying to give you some advice about how to draw these service boundaries, some of them are terribly, terribly wrong. Naturally, the one from Microsoft is the one that's terribly, terribly wrong. This is the picture they had of their first application. And this is from a blog on Microsoft about how to build microservices. So pretend like you have a normal single interior application that has the web, your business logic box, and your data cylinder over there. And a normal request just goes up and down. I can have one server for the website. Maybe the one server has my web and business logic, and then another server has my database. Now, if I get more traffic, then this picture needs to change a little bit. I probably have to have a load balancer here to be able to go to different front-end web servers. And then there's probably some sort of cache layer between that and my business logic. And there's probably some sort of cache layer between my business logic and the database. And in fact, this is a picture when I used to work at that company. This is the picture we had for our applications. Everything was load balanced. We were even doing blue-green deployments in the mid-2000s, being able to take things out of the load balancer, upgrade them, and put them back in, switching the other ones out. And this all worked absolutely great with this. The only thing we didn't get right was we were just directly using other people's code in our code base and directly calling their database from our database. But otherwise, this picture worked out for us well. Now, the blog post says, from here, in order to build microservices, you need to break each one of these tiers down into individual services. This is where they got their pieces wrong on the Bell side. They broke all of their services into different layers, and then in each one of those layers, they built out different boxes for each individual service. So on the website, they had different microservices for just rendering content. They had microservices for authentication. On the business logic side, they had orders and account information, things like that. And then, of course, on the data side, they had completely different microservices for all the different data pieces they had. So that the business logic was stateless, the web was stateless, and then here's all my data down there. Now, the reason why this picture was completely wrong for them was this did not actually map to any sort of business units or any sort of business need on the other side of IT. If we showed this picture to IT or to the actual business side, they would be like, I don't know what usage analytics means. There's no corresponding business unit over here. They had a number of services that were just made up just to further individuals' careers because you get more money if you manage more people, so let's invent a service so I can have people to manage, and then that's how I can further my career there. True story. So microservices was not just taking their interior system and then putting Docker on it. That is exactly the opposite of what they needed to do. Now, looking at a traditional interior application with my UI layer, my business logic layer, my data access layer in the database, or the much better DDD style interior where I have domain objects and a repository instead, I try to look at the different areas of change and different areas of responsibility. So in a normal interior application, I have different areas of change, and these are typically categorized by these different big vertical slices of the application. So in the original .com website, we had the catalog side, we had the configuration side, so when I clicked on an individual computer and said, okay, go ahead and configure this. Cart and checkout, that was the team I was actually on while I worked there. And the key thing we have to remind ourselves here is that for each of these different vertical slices, in order for them to maintain their autonomy, this boundary has to extend not only down to all the different business logic layers, but also all the way down to the database. So we had to do a little bit of a reset. Said, okay, clearly you try to build a service-oriented microservice architecture, but you got something completely off. So first of all, let's just reset what it means to be a service. And there's three sources I typically go to for trying to define a service. The first is the original service-oriented architecture definition of a service. And in that definition, we have a service is software that is owned and built and run by an organization. It's responsible for holding, processing, and distributing particular kinds of information within the scope of a system. Can be built, deployed, and run independently, meeting defined operational objectives. The independently there being one of the key words. It communicates with other consumers, presenting information using conventions or contract assurances. And then finally, or not finally, it protects itself against unwanted access and its information gets lost. And finally, handles failure conditions so that failure conditions cannot lead to information corruption. If you can kind of sum all these different pieces up in one word, it's autonomy. The services can be run independently of each other. They are able to meet certain constraints, and they define the contracts in which people can get information in and out. Of course, nowhere here it actually says a specific technology, and that's kind of the point. Now, on the microservice side, from the microservices book, the definition is a little bit simpler. It's a microservice is small and focused on doing one thing well, and it's autonomous. Again, we have that autonomous word coming back up. And they'd like to use the town planning metaphor. This is from the Microservices book by Sam Newman. And then the final definition I like to get to sort of round out what the service means is from the Domain-Driven Design book. Now, the DDD book is really long, and there's a lot of really useful information, but it's actually towards the end of the book that no one really gets to. So if you're going to read the DDD book, start at the part that talks about bound and context and kind of ignore the rest, because all that stuff about entities and aggregates and stuff like that is really just not that important. The bound and context piece are the most important pieces. The bound and context idea in domain-driven design says, I have a particular model, and that model may not make sense in different contexts. So a bounded context says this is the boundary in which this particular model can be applied. Inside that context, we have a logically unified model, and you can kind of see this in the business domain as well. If you go to your business and ask any one person, what's a customer? If you talk to the orders people, they'll have one definition of a customer. If you talk to the sales people, they'll have another definition. And if you talk to fulfillment, they'll have yet another definition of what a customer is. So bounded context says, right, we can't all agree on what a customer means, so let's define boundaries in which we can reason about what that term means, and then have translation points between those different pieces when I say, oh, you mean, we're talking about a customer, oh, in terms of an order, that means this. A customer in terms of sales, oh, okay, that means that. And, of course, it encapsulates any sort of internal operations, so that I'm not leaking those details to the outside world. And we also define explicit contracts for external communication. So, again, we have the idea of contracts that comes back in from SOA. And they typically use the cell metaphor, where a cell has a kind of a completely encapsulated set of operations and has specific receptors in order to be able to communicate to the outside world. So we came in and said, right, we cannot fix this entire mess, although you can pay us to do so. They didn't have the money for that. But we'll fix just one single service to make it sane. And from here on out, we'll be talking about that story of how we fixed at least that one service to make it actually respond to requests in a little less than 9.5 minutes, hopefully. So this is our search story. First, let's look at the microservice bell.com search approach. This was their design. Now, any external requests coming into the search site would have to go out to a number of different internal services to be able to pull those pieces together and actually present something to the end user. I only drew 4 boxes. In reality, there were about 12. And there's 4 arrows here, but again, in reality, there were about 200 arrows of things calling everywhere and going all over the place. So in this approach, they had a REST API, times about 1,000 or so different API calls. And the interesting thing about here is that the search site itself really didn't do anything. It just passed through all the requests to all these external places. So if I needed to search something, I would go and call the catalog site and say, okay, right, someone's looking for Windows 10 laptops. And naturally, the catalog site didn't have a search capability, so it said, right, we'll just select the top 10, where name, like, % thing, and then those are the things we're going to return. So around this time, if you wanted to go search, if you searched Windows 10 laptop on their search site, the first things that would come up were T-shirts and mugs, because those product SKUs were alphabetically the first thing in the list. Not extremely helpful in order if someone's actually trying to buy some laptops here. So we went back to the original picture of their architecture and said, right, so we have this catalog site, we've got this config site, and this cart checkout. What you actually need is this 4th service here for search. Search is its own individual thing. I said, but we can't have a search service because one of our key tenets was we cannot duplicate data. So how can I build a search service on top of this concept of no duplication of data? Well, you can't, because none of those other services have any idea how search is supposed to work. So you have to build a specific search service to be able to service those requests appropriately. So we went back to the drawing board in terms of their data ownership and said, right, so you've got this search service that needs to have data in a very specific format, but it doesn't own the data. But it needs to it actually needs to own the shape of the data, because the shape of the data is very important about how I need to be able to search it. search also needs to own the SLA of the response, not just in terms of how quickly responses get returned, but also the relevance of the different pieces that are being shown. So it needs to own the order in which things are being shown. None of the other services know or care about all that relevance information, so it really needs to be searched to be able to do so. However, it doesn't own any of the data that actually exists in those other systems. So from this, we realize, we can't have a system in which we don't duplicate data. And in fact, if you look at the real world duplicates data constantly. If you look at, you're just looking at a website that is duplicating some data in the server and showing it in the browser via HTML. So immediately, I have stale, duplicated data. Yet, we're able to function just fine as a society, knowing that I have information shown on my screen that may be a little bit old or duplicated. And that's fine. So we went back and said, okay, let's go back to some of the kind of core books that are around here and start to build a solution that's building off of some of these concepts. These are my three favorite books about these different subjects. First, Enterprise Integration Patterns, which is kind of a lousy name for messaging patterns, but it's really about messaging. The Sam Newman Building Microservices book, so we could say like, okay, don't believe us, but here's a book about it. And then finally, a little bit older book that's still relevant in microservices, which is SOA Patterns by Arnon Rodom Galaz. I don't know how to pronounce that, but that's good enough. And what we needed to do was perform service dependency inversion. And I put that in there just to troll Rob. That's just for you. So in service dependency inversion, in our original picture, we have one service depending on a lot of other ones. And it's depending on a lot of those other ones, not because it's wrong to depend on them. That's okay that my service can depend on these other ones. It is wrong, though, that my uptime is completely dependent on the uptime of all those other services. So we could take this picture and say, right, let's build resiliency in. So if I call catalog and catalog's slow, or if I call catalog and it's slow 3 times in a row, let's implement a circuit breaker pattern, and then we can have some sort of other cache locally. So we could do that. We could put caches and circuit breakers in front of all these different pieces, but that doesn't mean that I can still service an appropriate search response, because I still have to worry about the relevancy of the information. So we decided we wanted to flip these individual arrows around. So instead of a single request from the outside world calling a myriad of internal sources, we flipped all those arrows so that each of those other boxes would be pushing information somehow into our search.bell.com website, so that when an external request came in, I only ever had to go to a local database that was specifically built for the purpose of search, and no external service requests needed to happen. The biggest thing this did for us will be that it removed any sort of temporal coupling. That is, I don't have to worry about any sort of timing on any of these other external systems. If they can give me the information ahead of time, I only have to worry about my local database. I don't have to worry about any other person's uptime or latency or anything like that. So we just needed to break all those arrows and not piss anyone off. That was the other kind of thing we wanted to make sure we didn't do. There was a lot of people's careers on the line and this kind of architecture. So I said, okay, well, you can still do whatever you're doing, but we're going to try to make it better over here by not having a 9.5-minute latency. And if it works, then maybe other people can do it as well. So we went to each service one by one and said, okay, how can we break that arrow and reverse it to the other direction? And the Enterprise Integration Patterns book really told us the right way to do so. Our first service we were looking at was the catalog service. Now, the catalog service is interesting because if you go to shop online for some of these laptops, there's like a just insane number of configuration options available to you. You can have different processors, different RAM, different hard drives, different colors, antivirus or not, all this insane number of options, which is all done by a couple different services. In the catalog side, though, catalog was all about taking those complex configurations and saying, right, we need to print a catalog for someone, so why don't we have some standard configurations we can show people so they can say, yes, this laptop is $799, and that laptop has some standard configuration options you can change, but there's always some sort of default configuration. So although we had a lot of complex configuration behind the scenes, there were standard configurations that you could just go and click purchase. And those standard configurations are what gets showed up on any sort of catalog browse page. When I go look at, okay, what are all the laptops for education or for home office? there's a certain set of standard ones they typically show there. There's a known quantity of these different standard configurations. In our investigations, we found there was roughly about 1,000 or so of these well-known ones. If I tried to spread out and cache all the different configurations possible, it's probably more than the number of atoms in the universe sort of number. But if I had the known quantity of these specific top 1,000 that they just show on the website, that's something I can actually work with. So conveniently, the catalog site still had an old SOAP web service still up for internal applications. So we decided, right, what we can do is just once a day, ping that SOAP web service, get those list of standard configurations, and then store those results in our local document database. And if we need to change them more than once a day, then we'll have some back-end application be like, go ahead and update that one right now. So it was a rather easy one for us because they already exposed a service existing. The next one was a little bit more difficult. This was in pricing. Pricing is one of the services that if we went to the business, there was no business unit associated with pricing. Pricing was done typically by sales, or if not by sales, by a marketing group as well. They would work with multiple different organizations underneath the covers, but it still all went down to, I needed to have some really standard configurations of products. I need to work with supply chain to understand what's the good price to sell these at, what profit margins do we need to hit. But if I looked in the rest of the organization, there was no organization called pricing. It was something that was done by different groups. That was our first clue that something is wrong with the service because there was no analog to the rest of the and the rest of the business. And it's always funny to talk to some of the managers there about, so how do you get your requirements? Who are you talking to? Well, they just kind of made them up themselves. Again, that was another red flag. If you have a microservice that is really making up its own requirements without any connection to the business, it probably doesn't need to exist. So pricing, you might imagine, is pretty complicated. It depends on the configuration that you have. So as you select different options, the pricing changes. It depends on the region, which is, by the way, a trick on these websites. If you go change a region through like VPN and things like that, you may get better prices. Hint, hint. Also, if you pick like home office versus or business versus home, you'll get different prices as well. Something else to think about. And also dependent on the individual catalog, like I said, home versus business. We also found that it was actually served with the catalog information. So that previous web service we were hitting to get catalog information, we happened to look through the response like, oh, wait a second, there's a price there. Let's just use that. So we severed the connection and never called pricing ever again. And pricing said, that's great. Suddenly our API can respond well. We didn't actually tell them we were doing this. They just suddenly had much better latency because very few people were calling them actually. The next one we had to deal with was localization. This one was a bit tricky because even though the information rarely changed, there was a lot of it. So localization for us was basically not just showing things in the right locale and region for people, but also all the titles and descriptions and things like that needed to be correctly shown to each individual country and region. So although that information rarely changed, it was pretty large. We also saw that this localization service already served many, many internal clients. So there were already some existing sales applications and things like that had to use that localization information. And there's no way that all those different applications could change to use this new web API. So we had to look to see, well, what are all those different applications using in order to get this information out? Well, it turns out we could just use an existing integration method that everyone else was already using because they had forced the team to do so, in which once a day, they would put out a file on a shared drive that was just a flat file dump of their database that said, here's all the SKUs and all the translations of every single product detail information. So we said, right, we'll use that then. We'll go get that file once a day and just do a kind of bulk insert and shove that into our document database and call it a day. Now, our final one was the most fun one, the content one. Content one was also tough because it changed fairly frequently. And those changes actually needed to make it out to production pretty quickly as well. So it's important for us that when someone changed something in the existing service, we need to have it pretty soon afterwards in our database as well. This is what the business already expected. So we knew that the content service really wasn't going to change anything to give us like a feed of information. There was no Atom feed or something like that for us to subscribe to say, give us this information as it happens. But we knew the DBA pretty well. And after a bottle of whiskey, we were able to convince him that he could put some triggers inside the database for us. So when an individual table changed, we would get a message generated to feed into our search service that we would then take that message and then update our local document database. I don't know if the rest of the team still knows that this happened. They're just, again, the DBA is a pretty good person, and we bribed him with some good whiskey, so that seems to work well. Now, this kind of looks like a weird approach in that we have database triggers generating messages that we consume on the other side. But for something like this where I didn't want to touch the existing application, I didn't want to go put something on their Scrum board to have developed 6 months from now, I just want to have something done pretty soon, this is a fairly good approach. So for applications where I have an existing system where I can't really change that well, I'll resort to whatever means necessary to be able to get that information out. So what did this picture look like at the end? Whenever you did a search from the outside world, it only ever hit that one single internal document database. And then outside of that, on an offline set of processes, each of the other services would generate some sort of messages in some format, whether it was document messages or whether it was file kind of messages or whether it was trigger kind of messages, push these into a denormalizer that we would take all that information, process it, and put it into our local document database. That way, any requests from the outside, again, did not have to talk to any of the external services. And as long as we didn't change the data significantly that was coming in, we knew that, okay, for that data coming in, even though I didn't own it, I could still have a cache of it locally in our document database. So we did this, put it into production. The search website started behaving normally again. It went from a latency of 9.5 minutes to a more reasonable second or two, something like that. And everyone lived happily ever after, the end. Well, that's not true. So now for the not-so-happy ending of the rest of the story here. One of the things I've found over and over again with service-style architectures is that you can have success in one individual area, but that does not necessarily mean that you can spread that success throughout the rest of the organization. So I went back later and talked to some of the teams involved and said, okay, it's been about a year. How are things going now? Oh, it's great. We've got all these different individual services. Each of these individual teams that have ownership of the application, they have ownership of the database. They're all collated together. They heard DevOps was a good thing, so they brought operations into these groups as well. And everything was great. They said, but the problem was they still had the similar HR structure they used to have before. So even though each of these teams was able to build their own application independently, they were still run by crap managers. Because the only way you could get promoted in this company was, again, to manage more and more people. So that meant that the product teams had to keep growing, and the products themselves had to keep growing because that fit into the motivations of the individual managers of these different teams. And to a fault, every single one we talked to said, oh, the work is great. Man, we just keep adding new people to our team, and it just really sucks that everything used to be really small and focused, and now it just keeps growing and growing and growing. And again, that was because of the motivations, external motivations placed on each of these different managers. So there's not a lot of different ways you can fix this. If you look at applications like this, you'll typically see them built around what's known as Conway's Law, which you'll see this a lot in microservice discussions. Conway's Law said any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. And I see this absolutely all the time, that the systems we build more or less match the human systems that exist in the company. I don't think that's a bad thing, but you have to make sure that the motivations of the teams can allow this to be set up for success. So I have a corollary to this, is Jimmy's Law, which is a broken, dysfunctional organization driven by meeting unhealthy goals and metrics will produce broken and dysfunctional systems. This is exactly what we saw with them in the Bell example. Even though individual developers were all good people, because they were put into a broken, dysfunctional system with bad goals and metrics, then they will optimize the wrong things and build the wrong systems. Which is very strange for me, because when I first worked there about 10 years ago, I was on the cart checkout team. And our bonus for our team was decided on how many people came into the cart checkout process and completed the entire process. So my bonus wasn't based on uptime or SLAs or number of deployments or lines of code. It was strictly business-oriented. It said, the better cart checkout process you make, the fewer people will stop trying to check out. So we did a lot of fun things with this, like turned off all validations, because any red you put up in front of a customer will make them stop checking out. We used to have something that would check your credit card, like the loon check that checks the digits. Turn that off as well, confuses people. You put something in and there's like, oh, you put their credit card unit is wrong. No, you're wrong. Slam the laptop shut, go away. Well, if you turn that off, they're more likely to go ahead and complete the checkout process. The minimum stuff we did for meeting those operational goals of making sure everyone could check out was just, did they fill in all the forms? Did they fill in the first name, last name? Did it exist? Did they have all the required fields actually filled out? And that was it. Because, again, our motivation was to get people through the checkout process. Now, that meant, of course, that we had to do further processing after we got the information to say, ooh, actually, that credit card is invalid. Ooh, actually, that is a date in the past. Ooh, actually, that's not a valid shipping address. But we had all these things offline because, again, we were trying to optimize for getting people through the process. So we'd have help desk people call people after the door and said, ooh, looks like you may have mistyped that. And they were trained to be able to be nice and things like that, so that they could fix all the information and then go on from there. So if you have this crappy organization and you want to build systems for it, you're going to build crappy systems, because Conway's law is the law. So what you need to do is perform what's known as the inverse Conway maneuver, which is to design the organization you want, and then the rest of the architecture will follow kicking and screaming. Now, this is daunting, right? Because it says, basically, in order for you to build good systems, you may have to reorganize your company. And who's done that before? You're just a company of one sev. Does that count? Okay. So this building an application architecture like this can sometimes require buy-in at the highest level to say, it's not just our IT systems that are bad, it's our entire structure that's bad. We need to organize our company differently. We need to organize not just the IT people together, we need to have the business people in there. We have to have the operations people together and have those different groups align towards specific business goals. We need to make sure those business goals are not harmful and can cause bad things like building big teams, because that's the only way you can get ahead in the company. And it's only if that organization is healthy can then you build good systems based on those organizational structures. So that was my story of avoiding microservice megadisasters. I thank you for coming here, and I hope you enjoy the rest of the conference. And if you have any questions, I'll be happy to take them. Any questions? Yes?
What do you do if a service really does need to pop down the chain, or you should just avoid that altogether?
So the question is, what do I need to do if my service actually needs to make calls to multiple things? We had one golden rule that says I can only make one hop. I can make one hop from one service to another, but that service can't call anyone else. So if I have that case where I have to make multiple hops, either I've drawn my boundaries wrong, my service is not a correct service because I have too many dependencies amongst other things, or I need to invert those dependencies and start pushing that information to myself so that I can have it locally and not have to call those other people. Another question? How did I convince people that duplication of data is good? Well, one way to go about that is to recognize that we live in a world of data duplication. And in fact, their original business was built on data duplication, because there used to be a mail order catalog business. And that's millions of copies of the exact same duplicated data they've pushed out to hundreds of or millions of homes all over the world. So they've already duplicated data and built a business around it, so why is it any different now? So that was it. Like your business is already built around this. It's not like when you duplicate the data, they said, well, someone can change it. It's like, right, so when someone calls in saying they want to buy a computer and they said, yeah, the price isn't $799, it's $399. That's what it says in my catalog because they crossed it out and wrote something else. Like, no, you say, no, it's $799. So you can duplicate it just fine as long as you don't change it. Also, the 9.5-minute latency is like, yeah, you tried it, it didn't work. So let's try something that actually works. That helps too. Any other questions? All right, thanks. I'll be hanging out afterwards. Have a great rest of the conference.